Welcome to this module, to this video of Introduction to Computer Science and Python Concepts for Machine Learning. It's a very simple video just to get you started. Hopefully, you are already familiar with how to set up Google Colab. That's the easiest Python environment to get started with its notebook style formatting of code and ability to insert text cells and code cells and run each cell separately. So this is going to be very helpful if you have already set it up. I'm showing you my own Google Colab notebook. I will not be releasing this notebook because that's not a good way to learn. The best way to learn is to watch a part of the video, pause and try to type it on your own and run that part of the video. Even if you are just copying from the screen, the way the human mind works is that you will learn a lot more by typing it on your own as opposed to just running a code that is given by someone else. By typing, you will also make some mistakes in syntax, and those mistakes are also helpful in learning. So what I will cover is constants, variables and naming, conditions, functions, numpy arrays and linear algebra, while loop, for loop, vectorization, and the time complexity notation. Okay, let's get into it. So the first thing we'll talk about is constants, variables and naming. So actually there is so let's see if we want to uh, compute the area of a circle. If you want to compute area of a circle, I can simply write uh, that area of the circle is this string, which is pi times 2 radius squared, right? So if I run it, I will get the area of the circle, which is pretty straightforward. Okay, uh, but what you see here is there's a lot of hard coding. We have hard coded the value of pi, we have hard coded the value of radius, and so forth. So a better example would be that we give them um, variable names. So basically, pi is a, which is 3.1416, and the radius is b, which is 4. So the same formula goes inside a times b times b. Okay, but an even better notation would be to actually use this. Okay, use intuitive names such as capital pi I, okay, for pi, and then radius for 4, and then area for pi times radius. So that way, so there are a couple of things that are going on here. First of all, we did not hard code the radius. So if we want to change the radius and it is used several places in the program, we can make change in only one place, and we don't have to change all fours to fives, for example. The other thing is that there is no constant in Python. The constants are also variables, but the convention is to use capital letters for constants, so that you remember that it's a constant and it is not to be changed. So now if I run it, I'll get the same answer, but it is much more legible code. All right. Now let's look at conditions, if then else conditions. Here we want to find out whether a number is divisible by 7 or not. So if you look at this code, it's quite a messy code. What I have here is I first get x as an input. Okay, it's a number that someone enters, the user enters. All right, and then I will convert it into a floating point. I will divide it by 7 and check if I round it off, will it still be divisible by 7? Will it be same as if I just divide by 7? And if so, then it is divisible by 7, otherwise it is not divisible by 7. So if I run this, it will ask me for input. I can enter, let's say, 21, and it will say the number is divisible by 7. Now let me run it again. Let me enter 23, which is not divisible by 7. That also works fine. Now let's run again and enter 21.7. Okay, so it didn't check whether it's a whole number or not. And there's another problem here. If I accidentally enter some other input such as a, then the whole program will crash and it will give you a value error. Okay, so this few lines of code, it's basically lazy programming. And in this lazy programming, what you will see is that, let's say if there were no comments even, right, this would be completely lazy programming. So the lazy programming is fast, but it is fast if you just want that programming to be done for a day or a few days. The cons are that it's hard to understand after a week, it is inflexible, and it is error prone. What is inflexible here? We cannot repurpose this program easily to check divisibility by 12, for example. We will have to um, find all sevens and then change that to 12, and it is error prone. So compare that to this program, which is slightly lengthier, but it has a lot of good programming fundamentals. Okay, first we have different types of we assume that there are different types of inputs, and we catch any problems that we have with different types of inputs. We catch errors before they crash our program. Variables, we use variables instead of hard coding. Variable names are self-explanatory, and copious use of comments. Okay, and then you will also see nested if then else at work, and you should also so if and else go together, but if you have more than one else, then you can also use elif, which is else if. Okay, so first of all, we are checking divisibility by 7, so it's a variable div 7, div by is equal to 7. I can easily change it to 8, for example, and then I will get the input in x, enter the whole number. Okay, and if I want to make the above program even worse than what it is before, I will just say I can just even like not even have an explanatory comment here. So here I have enter a whole number to check if it is divisible by, and what is it divisible by? It is divisible by this variable, right? So this variable is 7. So I've converted that variable number into a string. Okay. Now I use something called try. Try basically catches errors. So it will try something. If there's an error, then it will go do something else. So there is try goes with except. Okay, and you can have multiple excepts. You can look it up the syntax for the try statement. So try convert x into a floating point number. If there's an error, then it is an issue. For example, if I enter a, then there's going to be an issue. But then there will be that value error that you saw, and I can print a error message, which is that you did not enter a number. Okay, so I convert it to float, and then I check, and if it is not divisible by if it is not the same as if it is not a whole number, then it will say that it is not a whole number, otherwise it will do the divisibility check. So you can see there are multiple if conditions, and if I run this, it is a much more robust program. If I enter a, it will say you did not enter a number. If I enter 21.7, okay, then it says you did not enter a whole number. If I enter 14, then it will do the regular divisibility check. Another thing I can do is I can easily change this to 12, okay, and run the program again, okay, and enter 48, and it will say the number is divisible by 12. So it is quite flexible that way. Now this the next concept is functions. If I have repetitive jobs, I can outsource them from the main program to functions. That will basically make the program more readable. So first let's read the main program. So this is the main program. All it does is it basically first I define the variable, which is 7, okay, div by 7, and then x is the input, and then I say check divisibility of x by div by. That's it. So this is very simple. This is a high level way of writing the whole program, and it is very so the function itself is very what do you call it, it's intuitively named, and then I go on top and do the heavy lifting inside this function. So this def or define is the way to define a function. So here there's a function check divisibility, which I'm using later, which takes two inputs, numerator and denominator, and then the code similar to the one that you saw before is here, except that I have these new variable names, numerator and denominator, which are more uh, easier to understand. So if I run this, the result is going to be the same, but this is how you should be writing your programs. Okay, so 21 is divisible by 7. Okay, so here another thing to note here is that you will see this underscore. This underscore, because this function returns value true or false. True if it is divisible, false if it is not divisible. Uh, Basically, if I don't have this, what will happen is it will also print true or false. You can try this. You can remove this highlighted portion and then run the program. You will see it will print a true or a false. Now let's go to Numpy arrays. Numpy arrays basically can be used to code vectors and matrices, and you can use linear algebra on them, which will be very important for your machine learning assignments. So NumPy is a library that allows us to do that, and it is convention to import that library. In C, programmers would remember this as include instead of include. Here in Python it is import. Import NumPy as NP. So we can rename the libraries that we import so that it is quicker to type and it doesn't take a whole lot of space. So NP, that's the convention. So I'm randomly starting some array. X is equal to a random array of size 3 by 2. So it's going to be a matrix of size 3 comma 2. Okay, so it's a random matrix. Now with this matrix I can do several things. I can compute its transpose, that is np dot transpose, and you can see that the transpose 2 by 3 sized transpose has been computed. There's another way of computing transpose, which is x dot t. So whatever is the array dot t, okay, dot t is also a transpose. So now keep in mind that this x dot t is the transpose of x, and now I'm taking its matrix multiplication with x. Okay, matrix multiplication with x. What is matrix multiplication? We do the command for that is dot dot. Okay, if we actually do x times x, it's not matrix multiplication, it is point-wise multiplication. So the 3 by 2 cannot be the 2 by 3 can be multiplied by 3 by 2 to give you a 2 by 2 matrix. This is what we got. Okay, but if you multiply the 3 by 2 with itself, it's just element wise square. So look at this, this 0.04 is the square of 0.21. Alright, now we can also compute pseudo inverse, for example. So for that we will get a module called linear algebra, which is in the NumPy library, and within that linear algebra linalg, there is a method, or there is a function called p inverse, pinf, for pseudo inverse. Okay, so if I do that over x, all right, I'll compute the pseudo inverse of x and multiply matrix multiplication. So that's why dot dot. I'll take its matrix multiplication with x. I should get the identity matrix. So it is nearly identical identity matrix. This vector is sorry, this element is 1. This element is 1. The off diagonal elements are very small. They are practically 0. They are e to the power minus 16. So that is because of the rounding off error in the multiplication program. Now let's talk about while loop. The while loop is the syntax is pretty straightforward. Uh, Basically, we write while, and again going back to the if also. There is no open bracket, close bracket. There is no begin or end in Python. Okay, you don't need that. What you do is, because it's a good programming practice to indent. So anything which is within the while loop, right? These lines are within the while loop. They're all starting with an indent, which is slightly to the right of where the while starts. So the indentation itself is indication to Python that it's a block within the while loop. Same with if, and same with try, same with for, etc. So that makes programming faster, and it is less prone to syntax errors. So there is no like curly bracket start, curly bracket close, etc. So here what you see, so you will see these helpful arrows that also tell you where you are in the block. So while the condition is true, keep doing whatever is in the loop. So basically that's what the while loop is. So here it's a guessing game. The program gets you a random integer between 1 and 11. 11 is excluded, so basically 1 and 10. That's just the format. In Python, a lot of indices are from uh, lower limit to upper limit plus 1. Okay, the upper limit plus 1, actually it takes minus 1 from there, and it doesn't include that plus 1 thing. So 111 would mean from 1 to 10. Okay. Same with indexing of arrays. Array indices start at 0, not at 1. Uh, Unlike MATLAB, they start at 0 in Python, and they go up to n minus 1. It's C style, but you write it as 0 comma n. You don't write it as 0 comma n minus 1. So that's how it is not like C. So here we will first try to get that number uh, from the user, and first find out whether it's an integer or not. If it is an integer and it is not same as that hidden number, then we will ask them to keep guessing again. Otherwise uh, we will say that you got the number once they get the number. So let's say there's a the computer already has a random number. Now I will enter 4. Okay, so 4 is not there. 5, 6, 7, 8, 9, 0, 1. Oh, okay, so the number was 1. I got 1. Okay, so that's how while loop works. Now let's talk about for loop and vectorization. So here what I will do is I will create a very large array, and I will have two nested for loops. Okay, so it will be a two-dimensional array, and I will find all the elements that are divisible by 7. Okay, so your x is so I'm taking uh, basically a random array of size 1000 cross 100, so it has 100,000 elements, and I'm so rand means it will be a uniform random pseudo random number between 0 and 1. I'm multiplying it by 100, so all the elements are between 0 and 100, and then I'm rounding it off. And then after that I want to find out, so this is a 1000 rows and 100 column array with random numbers, random integers between 0 and 1. So I'm running a loop, okay, for I in range the np dot shape 0, which means number of rows, and then j is the counter for going from for number of columns. So this outer loop, this loop runs from 0 to 999. This loop runs from 0 to 99. Okay, and then I have the indexing of the array xij, and I'm doing the divisibility check, divided by 7, round it off, multiply by 7, and whether it is the same element or not. If so, then I will do a plus 1 count. My count will be increased. You will see another thing that I have here with a library called time, import time. So here I am using a counter, tick and talk. Okay, and then I'm subtracting them, multiplying it by 1 million, and counting the number of microseconds that I have in the that I needed to compute everything between the tick and the talk. Okay, so what is the time to compute this, go through these two for loops? Okay, and here there's a way to format the strings percentage found percentage d element. So percentage d is an indication that there's an integer that will be given to be put in place of it. Found count elements divisible by 7 in percentage d microseconds. So what is percentage d? Basically this 1 million times tick minus talk. So tick talk is in seconds. So let's run this. So within those 100,000, it found 14620 elements divisible by 7 in 451,000 microseconds. Sorry, 541,000 microseconds. So here, look at this. This is expected. This is 1/7 of 100,000, roughly 1/7, right? Now let's see if we can make it faster. The whole point of this is how to make these for loops faster. So first of all, in that range, every time it was going through that I in range, it was every time it is computing this np dot shape. So it is computing this expression every time in the loop. So the way to shorten it is to pre-assign n rows and n columns and use those instead. So now these are fixed values, it doesn't have to be recomputed, only the variable has to be reference. Okay. So if I do that and rest of the logic is the same, it comes down drastically to 22,000 microseconds from 500,000 microseconds. Let's reduce it even further. Actually, we don't even need for loops. So this is the whole point of this exercise, that we can actually do this using vectorization. Every time you have certain things being done by a for loop, try to do it without a for loop. So here we know that this is a very large array. I'm sorry, this was one of the problems. So this is not 22,000 microseconds. Let's try it again. Yeah, so actually not much different. It is slightly different, but I had different numbers. That's why it was that big of a difference. 400 microseconds, and then roughly 500 microseconds. Yeah, there's not much difference, just slightly different. Now, but here we are not using the for loop at all. Okay, what we will do is look at this. This is actually doing the entire thing in one line. By using a vectorize operation. So how it is doing it is we are taking the entire array. Okay, for the entire array we are dividing it by 7. Okay, rounding it off, multiplying with 7, and then checking if it is equal to 7. So this is basically a true false. Now we'll get 100 by 1000 by a 100 array of trues and false. Trues and false, where false is treated as 0 and true is treated as 1. So we'll add up all those elements using np.sum. Axis.none means it's not like we are adding only the rows or the columns, we are adding the entire array. This is it. Within this one line, we have the entire count, and it is doing all the operations as much parallelizable as it can on all the elements of the array. Okay, it does. For loop will access each element individually, whereas here it will parallelize the operation if it can, using multiple cores of the CPU, multiple cores of the GPU, which we'll look at later. So now let's do this. And now the 500 microseconds has come down to 10,000, 500,000 microseconds has come down to 10,000 microseconds. The final computer science concept here is that this notation, which is order n. So anytime an algorithm is determined by some input size, here let's say the size of array is n, okay, and you have a sorted array of size n, which is let's say 100,000, and you have to find a particular element in it, right? So on an average, if you go linearly, first element, second element, third element, fourth element, etc., on an average you will take n by 2 time, which is proportional to n. Okay, so it is governed by n. Okay, so we call it order n. Order n means there's some constant k times n, and which will be the bound for upper bound for the time complexity, or even in the average case. Okay, so if we want to find that element, so here I have initialized an array of size n. I have sorted the array. Okay, and then y is some random element of that array. I've made sure that it's a random integer. I've picked something, and then it's a very simple program where I'm looking at going through it in the entire range, and if xi is equal to y, then I will break and I will say that I have found the position, the element in this position, and this is the performance time. So let's look at it. 400,000. Okay, so it found it in 83rd thousand in 18,000 microseconds. Now I can do it faster using a binary search because it's a sorted array. So in here it is sorted, and because it is a sorted array, I can have this logic, okay, where I have a lower index and an upper index, which initially is 0 and n. Okay, and I'm always looking at the middle element. I is upper, lower plus upper by 2 and rounding it off. Okay, so if the element is not found, then I will check if the current element is greater than y. If it is greater than y, then I will look at uh, the lower range. If it is less than y, then I will look at the upper range, and I will iteratively reduce that range by a factor of 2. Okay, because it is going down by a factor of 2, which is like exponential, the time complexity of this algorithm is in log n. Okay, so let's run this, and it takes only 227 microseconds. Okay, look at the position. The position is not that different, 75,000 versus 83,000. So it's not like it was the first one was too disadvantaged by position. We can run it again even. Okay, so 25,000 position, and then again 6,000 microsecond. And here the position is larger, yet only 182 microsecond. So here, because we are iteratively dividing our search space by a factor of 2, in general we will take log n steps, log to the base 2, but that doesn't matter because it will be absorbed in the base, doesn't matter because it will be absorbed in the constant. So in general, if we have the larger the array we have, the the algorithm that I showed before, where we were linearly searching, will scale up proportional to n. So we write its time complexity as order n. Here, the algorithm will scale, the time will scale as order log n, because it will scale up as log n. Because even if you, so let me change this. So let's say if I change it to million, uh, this microsecond 182 microsecond will only go up to 200 microseconds or 300 microseconds. Wow, this was very quick. Yeah, look at this. Even with the million, it is faster than the other one. Okay, so where to go from here? This is all that I have to teach. You should look at classes for object-oriented programming. That's a little more advanced concept. You can wait to learn classes later, but you should definitely learn to search for different things that you want to do in Python. Type it in a search engine and look at how look at various tutorials and learn from them on your own. Thank you.